At this point in the proceedings, I usually say I'm delighted to welcome this afternoon's speaker. I'm delighted to welcome this afternoon's speaker. As you know, today is the presidential address, and so I'll be giving the talk today. Now, as most of you know, I've worked for a number of years with a mission known as the Herschel Space Telescope, and I'm going to tell you a little bit today about some of the things we discovered with the Herschel Space Telescope. Now, the field of research in which I work is the field of star formation. So trying to answer the questions of how stars and planets form in the first place. And this was one of the key questions that the Herschel mission was designed to try to address. So what I'm going to tell you about to start with is a little bit of the background of can we possibly have the lights down a little bit, please, Robin? A little bit of the background about what we knew about star formation, how stars form before Herschel flew, just to set the scene, and then I'll tell you about the Herschel mission itself. It finished just literally earlier this year. We're still analysing the results from the mission, but already we can tell it's made a difference to our understanding of this field, and I'll try to explain to you what we think we've learned. This is all very new and very hot off the press. Our team presented this work literally only just over a week ago at a conference in Heidelberg, where the world's astronomers were assembled to discuss what we knew about star formation, and the new paradigm that I'm going to outline for you was what we presented at that meeting. So it's very much the very latest things that I'm going to be telling you about. Now, here's a question for you. Why are stars the size they are? Have you even thought of that question? Why? They just are, aren't they? They're just stars. The most fundamental observation in astronomy is that when you look up at night, there are stars in the sky, okay, on a clear night. Now, it might sound like a stupid question. Well, of course they're the size they are. They're stars. That's what makes... Well, no, it's not really, because if you think of the sort of size range, the ranges of mass that we know about within the universe, it's a very, 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 very large range. The smallest sort of particle, if you like, of fundamental particle that exists on its own, the electron, has a mass of 9 times 10 to the minus 31 kilograms, or as it says up there, 0.3009 kilograms. That's quite small. That's quite a low mass. At the other end of the scale, to a first order, what we can see in the universe, the mass of the observed universe, is something like 10 to the 54 kilograms. A 2 with 54 zeros after it. So that's 85 factors of 10 between the smallest thing we know about and the biggest thing we know about. Within those 85 orders of magnitude, stars only occupy about 2 or 3 at most, okay? And that's the absolute extremes, somewhere between 10 to the 29 and 10 to the 32 times 2. So a 2 with either 29 zeros after it up to 32. Or to put that in a sort of pictorial form, slightly cartoon-like pictorial form for you. Along the line there, those of you at the back may not be able to see, but I've drawn a whole series of dashes. Those are our 85 dashes. There are 85 dashes there, one for each of the factors of 10. So starting at the left, you've got the electron, and at the far right, you've got the whole universe. And each time you move along a dash, you move another factor of 10 bigger. So you get to about a kilogram, and around about us in the middle there, and then where I've marked the star symbol, that's the mass that stars occupy, the mass range. Very, very narrow range of masses. Why is that? Okay, we'll come back to that in a minute. Then you go a few more orders of magnitude further along, and you get galaxies. So why is it that when matter gets together on that scale, it forms a galaxy, rather than just a very, 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 very big star? Have you ever thought about those questions? Okay, well let's think about those for a minute, because it's the fundamental observations of that sort that really kind of drive everything else. Well, we think we know why there's an upper limit to the masses of stars. And it's to do with how stars evolve. You're all familiar, I'm sure, with stellar evolution, and if you have a very massive star, it finishes life by exploding in a gigantic supernova, blowing material all over the universe, and the little bit that's left falls back in on itself. And as long as it is only a little bit that's left, it forms what we call a neutron star. And a neutron star is literally one big ball of neutrons, nothing else. It's been pushed together so densely that all in the atoms, all of the electrons have been forced into the nuclei. Such is the force in the centre of there. And all of the electrons have combined with all of the protons, and all you're left with is neutrons. And it's the neutrons pushing against each other that stop the star from collapsing. And the limit for that is around about 3 times the mass of the Sun, slightly more, around about 3 times the mass of the Sun. And that's a fundamental limit. If you get more mass than that together, then the force that holds neutrons apart, which is the strongest of the fundamental forces that we know about, actually fails. You get so much mass, and we get what we call a black hole. Because there is no other force in nature that can hold that star up against gravity. Gravity wins in the end, and you form a black hole. We have reason to believe, or at least a number of astronomers believe, that in the very early universe you did form very, very, very massive stars. But they evolved so quickly, because they were so massive, they went kablooey very quickly and fell back and formed supermassive black holes, such as the one we know inhabits the centre of our galaxy, and most similar types of galaxies. So the reason we don't see many stars like that is because they just don't live long enough. Basically, they just don't live long enough. They're gone in the blink of an eye. And so even if there were more massive stars than this range we see today, they've all gone. And there's one theory behind these so-called gamma ray bursters that I'm sure you've heard about, that it is that gamma ray bursters are these supermassive supernovae. Some people have coined the phrase hypernovae that happen in the early universe from these really, really, really massive stars. So the stars that are left around today, and even the stars that form today, they have an upper limit that's really determined by this upper limit for neutron stars. So that's the top end. That's why we think we don't see stars greater than a few tens of the times of the mass of our Sun. Solar mass. I'll come back to the lower limit later on, because that's equally interesting, but for very different reasons. Next fundamental question: why are stars so far apart? And for this we have a little demonstration, and I'm going to ask for my assistant from the audience to come out and hold up a tennis ball. This is George, by the way. George Alexander, the first George Alexander, not the imitation one this week. So if you hold the tennis ball up, please, Your Highness. If we shrank the Sun to the size of that tennis ball, you've all heard things like this before, where is the next nearest star? Well, we had a debate about this on the train coming here this morning, involving measuring the tennis ball and Googling different places. Where is the nearest star? Is it in the UK? Is it in London? Is it in this building? Trafalgar Square. That's a good guess. Higher or lower?
Higher.
New York? The moon. Higher or lower than the moon? Lower. Lower. The answer we came up with was approximately Gibraltar. So, if you take stars to be the size of a tennis ball, okay, Proxima Centauri is in Gibraltar. Voyager, that was launched about 40 years... You didn't sit down yet, George, you haven't finished. Voyager, that was launched about 40 years ago, has travelled further than any other human-made object. It's reached the edge of the solar system. On this scale, that's somewhere towards the North Circular. Okay, that's not even snail's pace. A snail could get here from here to the North Circular in less than 40 years. That makes snails look fast. Okay, stars, relative to their size, are a long way apart. Why is that? Well, the stars that we know, such as the nearby ones to us, all live in our galaxy, which we call the Milky Way. As you know, the Milky Way is roughly saucer-shaped, and George is going to now hold up a saucer for us to remind us the Milky Way is roughly saucer-shaped. Cue saucer. Now, next question. Suppose I took the Milky Way and squashed it down to a single sheet, okay, to the thickness of a sheet of paper. How dense would it be? Okay, I'm not changing a scale here. This isn't pretend the sun's a tennis ball game. This is the actual numbers. Okay, it will be a sheet of paper 100,000 light years across. Okay, but you take all of the stars and all of the gas and dust in interstellar space, you smear it all out till it's totally uniform, and then you squash it down till it's the thickness of a piece of paper. What density would it have? Okay, well, if I took 1 square light year, so imagine a light year, I cut a square out of the Milky Way, 1 light year by 1 light year square, I would have typically about 4 solar masses, 4 times the mass of the sun. So the density is 4 solar masses per square light year. Okay, if you change the units of that into grams per meter squared, you get 80 grams per meter squared, which is about the density of paper. So if you took the galaxy and you squashed it, you didn't change the scale or anything, you just squashed it down to the thickness of a sheet of paper, totally smeared about, it would have the same density as ordinary photocopier paper, about 80 grams per square meter. That's why stars are so far apart. You need an awful lot of sheets of A4 to make something the mass of the sun. Okay? That's why they're so far apart. Because the actual density of material that they're made from is relatively low. So, one final question. How far apart are galaxies? I think we've got 2 sources. George's mother wouldn't let us out with any real ones, so we got the plastic ones. So, suppose George is holding up the Milky Way, and I've got Andromeda, or the other way around, it doesn't matter. Disk galaxies. How far apart should they be? If George is standing there, should I be standing in Gibraltar? No. Bit closer than that, isn't it? Trafalgar Square? No. The North Circular? In actual fact, we're standing about the right distance apart. Okay? Not even in a different room. We're in the same room. Galaxies relative to their size, are relatively close together. Stars, relative to their size, are relatively far apart. And the reason for that is stars are a heck of a lot denser than galaxies. And as I said, you need a lot of sheets of A4 to make a star, whereas only one thickness of A4 to make a galaxy. Okay, we'll leave that at that for a second. You can have a sit down now, George, for a minute. Give him a round of applause, please. Oops. Thought I tripped over a cable. Now, there's a nice picture of Andromeda. This picture is actually an infrared picture. This is the first picture from Herschel that I'll be showing you. Beautiful spiral galaxy. You can see the spiral arms in the infrared as well, because that's where the material is denser. It's on average denser than the average. Here's a fairly familiar sight to most of you, I'm sure, the Milky Way galaxy, that part in Sagittarius towards the galactic centre. The dark lanes that you can see, that's all the dust and the interstellar clouds where the next generation of stars are going to form. And those are the things we're going to concentrate on today. Incidentally, I couldn't resist showing you this picture, which is just a slightly smaller area than the one you're seeing here. We're closing in on the sort of red area in the red triangle in the middle of there, which I hope you can see. And I hope you can see a kind of figure of 8 shape on its side, a sort of infinity shape. That is a real structure. That is a real structure of material orbiting the centre of our galaxy in a really strange, convoluted kind of figure of 8 orbit. That was discovered by Herschel. We believe it's clouds of gas and dust in a resonant orbit around the black hole in the centre of our galaxy. That was one of the first Herschel results that weren't predicted, shall we say, in advance. One of the unexpected results that came out of Herschel. So, just a little bit about background now. Here's a cartoon. This is roughly how we think stars form. You have those dark lanes that I was showing you the picture of in the Milky Way. They form slightly denser regions in the top left-hand figure there. Those denser regions collapse to form stars. The stars have winds and they have disks around them, just like the sun has a solar wind and it has a disk around it. No, it doesn't, does it? Well, yes, it does. You're all sitting on it, or what's left of it. The planets form out of the disks around the stars. You notice right at the very, very end, I just lifted this from one of the standard texts in this field. Right at the very, very end, the person who drew this cartoon has put one little question mark right at the end. He wasn't 100% sure of what he was doing, but that was his best guess as to what was going on. Now, there's an awful lot in that isn't understood. First of all, where do those things come from in the first place? Given that you've just got this mush of interstellar clouds and what have you, why do you suddenly form bits there that are dense enough to collapse and form stars? That's not known, or at least it wasn't. And I'm going to try and convince you that we think we now know how that happens, thanks to Herschel. The next question is, how do you go from that stage to a star? Now, I know I'm talking to an educated astronomy audience here, and I know you've all done a lot of reading in astronomy. Somewhere in among that you'll have come across things such as the Jeans mass. Hands up all those who've heard of the Jeans mass. Yeah? Or the virial mass, which is just, similar again. It's just an extension of the same sort of idea. Well, this is where our friend Hoppy comes into play. Okay? And this is where we need George again, please. Because we can demonstrate this using a space hopper. Yeah? The Jeans mass. Demonstrate. I'm sure Sir James Jeans didn't use a space hopper, but is it just me, or have they got smaller over the years? I remember them as a lot bigger than these back in the 70s. When, you need to put the people at that side can't see you, George. Come over here. Thank you. Hold it up. There we go. It is a junior one, apparently. It was easier to fit into George's bag on the train this morning. Yeah, right, are you going to demonstrate how you use a space hopper, George? If you've got space, without bursting it, hopefully. Thank you. A space hopper. Yeah, you all know. Right, why does that work? Inside, you've got pressure holding it up. Yeah? On the outside, you've got George bouncing along to go down. Now, I'm not going to try this experiment, but I can assure you if I did that, the damn thing would burst. Okay? And my posterior would hit the floor, and that's what we call gravitational collapse. Okay? The reason these things collapse is they're being held up by their internal pressure. Those are basically the thing in the top left-hand picture of the cartoon. Think of them as a bunch of space hoppers in space. Okay, they're quite big. You know, they're a few tenths of a light year across. They're fairly biggish things, but they're just space hoppers, really. Okay, and they don't have plastic outsides, but they have sort of really reasonably well-defined edges. And the thing is, if there's enough mass, perhaps a great lummox like me, pushing from the outside, they'll collapse. If there isn't, George, they'll stay up. They stay inflated. And the gene's mass is the mass required to make the space hopper collapse. Okay? So if ever you read, you know, complicated stuff in textbooks that's trying to pull the wool over your eyes about the gene's mass or the virial mass, just think of the space hopper. It's really nothing more complicated than that. It's a balance between pressure holding it up and gravity making it collapse. And so the second picture in the cartoon, we think we already understood before Herschel that if you've got enough mass, the space hopper will collapse. But we still didn't know where the space hoppers came from in the first place. And that's the question that we set about addressing with Herschel. Thank you again, George. Give me another round of applause. Risking life and limb bouncing across the stage. So, let's have a go and see if we can understand where the space hoppers come from in the first place. One other fact about why we're interested in the space hoppers, don't worry about the details of this. Basically, all I'm doing is plotting a bar chart in a weird way. Okay? You've got a number up the side on it. Instead of putting a bar on it, I've just drawn a line over the top of it. We have known for many, many years that the relative numbers of low mass stars and high mass stars remains unchanged pretty much wherever you look. This was first discovered by a chap called Salpeter. Who's heard of Salpeter and Salpeter's law? One or two of you. Okay? We've known about that for about 50 years or so, maybe a little bit more. And nobody really knows why, and that still hasn't changed. Nobody really knows why you get the same ratio of low mass stars to high mass stars. But what we found out shortly before launching Herschel was the space hoppers show the same mass distribution as stars. Okay? The relative numbers of high mass space hoppers and low mass space hoppers was the same as the relative numbers of low mass stars and high mass stars. And that's all these two curves are trying to show you. What that means is that the mass of the star that you form at the end of the day depends on the mass of the space hopper you started with. So yet again, this is just another argument for why we really crucially need to know where the space hoppers came from. Okay? What formed these clouds, or rather cores within the clouds in interstellar space. So, May 2009, 14th of May, Herschel is successfully launched from Kourou in South America at the European Space Agency's spaceport. That all sounds very glib. Can you imagine working on something for about 20 years, so half your working life, polishing it and making it as absolutely perfect as you can for 20 years, and then some lunatic takes it off you and straps it to the top of a Guy Fawkes rocket? Okay? That's what the guys felt like who'd built this thing. Yeah? You've all seen the pictures from the first Ariane 5 launch, that launched cluster. That really was a Guy Fawkes rocket. Okay, at the time I was working at Cardiff University, and Cardiff built one of the three cameras, that went on this telescope, and so I was alongside guys who were in exactly that position I've just described to you. They've been working on this thing, and some of them basically since they graduated they had done nothing else, okay, but work on this one thing. We had a special launch party, and being Wales, we invited a few Welsh Assembly members. The First Minister for Wales was there, and so on, and we had a big party, and it was the most nervous bunch of individuals you have ever seen. We had a live feed from Kourou, and we watched the launch, but it went off absolutely impeccably, of course. Now, the mission was designed to be a 3-year mission, was launched on the 14th of May 2009. It finally ceased operations on the 29th of April this year. So we got almost 4 years out of it. So not only did it match expectations and reach its goals, it actually worked for about 30% longer. So we got even more data than we were expecting, which was absolutely tremendous. And the only thing that caused the end of mission was that it ran out of cryogenic helium. If you're taking pictures in the infrared, the one thing you don't want around you is heat, because heat is infrared, yeah? So if your telescope is sitting there warm, then it's like taking an optical picture through a telescope made out of fluorescent light tubes, yeah? You're not going to see a heck of a lot. So everything's cooled down, and especially the detectors, the cameras. The telescope was just passively cooled, but the cameras were all cooled using liquid helium, and they were cooled to a very small fraction of a degree above absolute zero. So somebody tried to describe to me the sort of heat levels that we were trying to detect with this. Suppose we go back to 1969 and Neil Armstrong's standing on the moon, and he's got a bell jar with some oxygen in it and a flow of oxygen, and he strikes a match inside that bell jar. This thing, if it had been here on Earth, would have been able to detect the heat from that match. Okay, that's the level of sensitivity that you're talking about. So it was really the most sensitive instrument that was ever launched, and it was actually the biggest telescope that was ever launched, 3.5 meters in diameter, way bigger than Hubble. Not a lot of people know that, and I really don't understand why people talk about Hubble, but Herschel was much bigger. So what did we see? Well, being predictable astronomers, let's look at our favourite objects. Go on then. So here we start in Orion. I'm sure you all recognise that picture. That's a typical optical image of Orion. I'm going to overlay on it the previously their best infrared picture that had been taken of Orion. That was taken with IRAS, the infrared astronomical satellite that flew in 1983. Relatively small telescope, but extremely successful, mapped the entire sky in the infrared. And I'm going to zoom in on a little bit of it down here. You notice the belt stars were over here, and we were over in this one over here. Yeah. And notice down here, this is your favourite Orion Nebula, yeah, your favourite telescopic object. And then just zoom in a little bit, and I'm going to zoom in just on this bit. Remember, the Orion Nebula's down here. I'm going to zoom in on this bit here. There's the square that I'm going to zoom in on, and I'm going to turn that square on its side so it fits long ways across the screen and show you the picture that Herschel took of that area. So it's quite dramatic. Now, whenever you're taking a picture in the infrared, of course, you've got a problem that our eyes don't see the infrared. So how do you display infrared? Well, what I've got here is I've got 3 different wavelengths of infrared, and I'm representing one with red, one with green and one with blue. The shortest wavelength with blue, the longest with red. So if your eyes were red, green, blue sensitive to the infrared, this is what it would look like. Okay, that's how I'm demonstrating the colours. Now you've all already spotted that it's one of your favourite objects. This, by the way, isn't the horse's head. That's it there. Do you all see it? That's the horse's head there. So this is about 4 degrees across. Okay, it's just a typical field that Herschel was able to image. And what you're seeing here in absolutely unprecedented detail is the structure within these clouds in interstellar space. If ever we're going to understand how they form their cores in the middle of them, their space hoppers, we've got to understand the structure. We've got to understand what that structure is and how it evolves. And that was the problem we'd set ourselves, and that was what we were trying to look for. So that was just one image, that's just one area we looked at. We mapped quite a few. Oh, before I go on, the horse head, I'll show you it again over here, and I zoom in on that bit. This was a pre-Herschel picture. So on the left is just an ordinary optical picture. On the right is a ground-based, very far infrared picture taken with the James Clerk Maxwell telescope in Hawaii, which I'm sure some of you have heard of. Again, false colour. I won't labour the point about false colour, but whenever I show a far infrared picture, I'll be showing it as if your eyes were sensitive to the infrared in false colour. Now notice the familiar sort of horse's head shape. You see that in the infrared as well. Minor technicality here, you're seeing it dark, you're seeing it as a silhouette. Here you're seeing it bright, it's shining. It's about 10 or 20 degrees above absolute zero. That's hot. Okay, to Herschel and the far infrared, that's hot. So you can see it. And what's more, you can see into it. And so even though there's really very little here at all, you can see suddenly here. And we published this paper a few years ago now, and the title we gave to the paper was, "What did the horse swallow?" It literally looks like it's taken a tablet, doesn't it? And he's just in the process of swallowing it, and somebody took an x-ray of the horse. We think this thing is one of those cores that I was talking about earlier, one of the space hoppers. And this is one that's recently formed but hasn't yet collapsed to form a star. This was the sort of typical infrared picture, far infrared picture we had of these clouds before Herschel. Then along came Herschel, as I say. This is an image 3 by 3 degrees, so 3 degrees on a side, 6 full moons wide by 6 full moons high, so it's another quite large area of sky. This is in the constellation of Aquila. This was actually the first image that came back for our own survey, the first one we got back, and frankly, to put it in scientific terminology, we was gobsmacked. The pictures were just absolutely amazing, and the structure on every possible scale in this picture that you could see was just absolutely tremendous. If you look deep into this, a small part of this is just, I'm using a different colour scale on the right just to, I lost the button, there it is, to show this. On the left, this is a near infrared picture taken from a previous telescope, and we could already tell there was a young cluster, a young star cluster forming in the middle of this cloud. But why has it chosen to form here? Well, you can see these dense regions. Again, you're seeing the same dense region, but whereas here you're seeing them in silhouette, or extinction as we call it, here you're seeing them emitting. You're seeing them in emission. You're actually measuring the heat that they're giving off at their 10 or 20 degrees above absolute zero. This is another one of my favourites. This is Taurus. This is now a single wavelength, so I've just shown it in a single colour. Now we're something like 10 degrees across. So Taurus is at a distance of, let me get this right, about 360 or so light years away from us. And if that's 10 degrees across, then that means you're looking at something about 60 light years across, okay, at the distance of Taurus. So you're seeing a huge region of sky. And what we're also seeing is that it's all connected. It's all connected. And all of these weird and wonderful structures on all sorts of scales. So we started calling these things filaments, because we were seeing filamentary structure in the clouds. We started calling these filaments. But then you also see little filaments coming off the big filaments, and the big filaments making bigger filaments, and so on. But everywhere you look, you see this filamentary structure. I think the next picture is just a zoom in of one part of that. I keep changing the colour table, basically just to keep my own interest, shall we say, when we're making these pictures, because a lot of these maps do look very, very similar, with lots and lots of fluffy structure. That must mean something. That must be telling us something. What's it telling us? So we kept going, we kept looking at a few more. Now, let's point the telescope at Polaris, the pole star. Right up at the top, right up north. The Polaris is about here, okay? And there's even woofly stuff around there, around Polaris. It's very, very faint, very, very faint, but nonetheless Herschel could see it. And again, you see these kind of filamentary structures, much, much less dense. Much, much less dense. So, is that telling us something? Well, there is no current active star formation in the Polaris region. There are no new stars being formed there at the moment. And that region is very much less dense than Taurus or Orion, where I was showing you before. So there's a clue. Density. You need the density to get the mass to make the stars. So there's one of the clues. And I think we spent some time, if I remember right, looking at this bit here, where it looked like there was sort of knots in the filament and a sort of a loop. And then there was another one over here where you see other loops. Now these loops had been known about, and filamentary, there's one of them. This is just to show you, by the way, this is to demonstrate what I mean about how I put together a 3-colour image. Yeah, 3 different wavelengths and representing them with red, green and blue. You chuck them together and you make just the same as in your colour telly. Or at least the old colour tellies before we all had LED flat screens. The old ones where you had the 3 coloured dots if you look close enough at the screen and made yourself go blind. Just exactly the same way, and that's how we're making these pictures. When we are making these, wherever you see something that's very bland and grey like that, that means it's roughly the same brightness at all wavelengths. If you see one wavelength dominating over another, you'll either see a region that looks blue or a region that looks red. And that also helps you, because colour, just like in everyday life, colour also tells you about temperature. Something that glows white hot is hotter than something that glows red hot. Yeah? So colour tells you about temperature as well. So we've got some clues. We've got clues about density, and we've got clues about temperature. This is just to show you, Herschel didn't actually discover this loop. It was previously known about, but not to anything like the same level of detail. And just one other issue, before I leave the subject of Polaris and the pole star, just to tell you about Herschel, and particularly this camera, the one that was built, led by the team from Cardiff. It was called Spire, and I've taken the blankest bit of this field that I can. If you look pretty much straight up to the North Pole, you're looking pretty far out of the plane of the galaxy, and pretty much to one of the blankest fields you can. And if you blow up the density, the intensity contrast in this image, you suddenly see it going spotty. Okay, so you think, all right, well, we've reached the limitations of the camera. Not true. Those spots are not noise, they're all real. They're all distant galaxies, very distant galaxies. So the limitation of how good the pictures are that we can take are not limited by the camera, they're not limited by the telescope, they're limited by the universe itself. The universe itself is spotty when you get to that level of depth, because everywhere you look there's a very high redshift, very distant galaxy, and that's what all of these dots are. Okay, so that was how good a job they actually made of building this camera, which amazed me when I saw it. As I say, I thought we'd had a black hole. Amazed me when I saw it. I thought we'd reached the limitations of the camera, but no, we've reached the limitations of the universe. Oh dear, he's shown us a graph. Oh heck. Don't worry, don't panic. Don't worry about the details. Just like when you used to do experiments at school and you plotted some points, that's what the circles are. The straight line is a theory. Okay, don't worry what the theory is. Okay, here's another graph. Again, the dots are the data points and the line is the theory. This was known about long before Herschel flew. Which of those theories is better? That one, where the points are closer to the straight line. That's all I wanted you to notice from these two graphs. Okay, that one involves magnetic fields. So we already knew before Herschel flew magnetic fields were going to be important as well. So that's another clue. I love this one. This was a picture taken also from the ground before Herschel flew. This was also taken from the James Clerk Maxwell telescope, but it's actually a series of spectra. Every single dot on this picture has a spectrum associated with it. So what we can then do, so on the left hand side I'm just showing intensity as before, but on the right hand side we can separate out red shifted and blue shifted. Okay, red shifted is going away from you, blue shifted is coming towards you, so you get velocity. So you see the stuff coming towards us, going away from us, all over, going sideways and what have you. I wanted to call this the Kablooey Nebula because it's basically just gone kablooey and blown itself apart. Yeah, it's formed in the center of it a huge cluster of stars, and those stars, being young, are very, very energetic. The sun we sometimes think is energetic, where you sometimes get solar wind, solar storms and so on. It's nothing compared to young stars. The winds and the jets and what have you that comes off young stars, tremendously energetic. Hundreds and hundreds of kilometers a second of velocities coming out of these things. Literally rips the cloud apart. So as soon as you've formed a bunch of stars, kablooey, if you form enough, you blow the cloud apart. But that also is going to lead to some kind of chaotic structure in the clouds as well. So we know that folds into it. We call that turbulence. Okay, turbulence. We knew turbulence played a role before Herschel. We knew magnetic fields played a role. We knew that the structure played a role, but we didn't know what. Now, there was something in I'm back in Taurus again now, hopping all over the sky for you. Back in Taurus, there was something that was known as the Taurus molecular ring. Well, we actually debunked the fact that it was a ring. There's nothing ring-like over here. But over here, you have got one of these filaments. This was known about, again, before Herschel flew. We published it the year before Herschel was launched. We actually, you get the impression that sometimes we have particularly slow days. We called this paper pulling the bull's tail, okay? Because basically we called this the bull's tail filament. So even before Herschel, we knew there were filaments. So don't go away with the impression that Herschel discovered filamentary structure. It was already known about. I'm sure you've seen plenty of pictures of it before. What we didn't know was what role that plays in the formation process. What role does that play in forming our space hoppers? Oh, don't worry about this. This is just another picture of the bull's tail, trying to show you that it's actually incredibly dense, because even at a very long infrared wavelength, which is 10 times as long as the red wavelength, you're still seeing it in silhouette. Okay, normally by the time you get to these sorts of wavelengths, nothing's in silhouette anymore. You see right through everything. But now we're still seeing it in silhouette. So density is a real clue. And that's all this was supposed to show, by the way, that you're still seeing it in silhouette. This was a one-dimensional cut going crossways across the bull's tail at each of the different wavelengths, just showing that you're seeing it still in silhouette, which tells you how dense it is. So back to Herschel. This is one of my favourite Herschel pictures. To me, it looks more like a Turner. You know, you're expecting the Fighting Temeraire to come sailing in the right-hand side there as you're going on this tremendous wave. It makes you want to get out on a surfboard and go and try and ride that gigantic wave. What's causing this? Well, it's kind of the next stage on from the Kablooey Nebula. Yeah, down here in the gap, you've formed a bunch of stars. They're just out of shot there, deliberately. You formed a whole bunch of stars, new stars. They went kablooey, like the other nebula that you saw. But once they've blown the nebula away, you're left with a hole, a cavity, and that's what you can see here. You're looking into a cavity in these, in the cloud, but also, again, you're forming these sorts of filaments on the edge of the cavity. And in the tips of these filaments, there's some evidence that you're forming cores, the space hoppers. Okay, in the tips of the filaments. So again, that's a clue. So we've got temperature, we've got pressure, we've got density, we've got magnetic fields, we've got turbulence, we've got chaos basically at the moment. How the heck do we put it all together? Here's another picture. This is part of the galactic plane. Again, the three-colour image. Again, you're seeing these sort of filamentary structures and stars that are already forming and have blown out cavities and so on. Basically, the message I'm trying to get is just another part of the galactic plane, just a single wavelength. The message I'm trying to get across to you is there's filamentary structure everywhere you look. Filaments everywhere. And look at this one. You see this great long filament. It seems to fork up here, and then coming off the side of it in each direction is little filaments. Well, we couldn't keep calling everything filaments, so we had to come up with another word. So we called them striations for no good reason other than it wasn't the word filaments. So we call these little ones, in a sense, we thought of them as feeder filaments. And that gave us a clue. That gave us a clue as to what's going on. Let's try and put it all together. Okay, so here's, I think I'm back in Taurus again, sorry, jumped around. We're back in Taurus. This was one of the ones I showed you earlier in Taurus with the little striations coming down. The lines are just on there to kind of guide your eye for the filamentary structure. And here's the main filament. And then the little striations. The green lines on here, they aren't Herschel measurements, they were previously taken. They are measurements of the magnetic field. Okay? The magnetic field is going along the striations, not along the filaments. And that's another clue. Furthermore, we found that something like 2/3 to 3/4 of all of the cores were on filaments. So all the space hoppers live on filaments. And what's more, a lot of them form, and the biggest ones, form at the junctions of filaments. This is a close-up of that bit in there on this left-hand one. Half a parsec, multiply that by 3 and a bit, 1.5 light years is that arrow there. Okay, so still big scale stuff. But nevertheless, I think this one's back in Aquila, just to keep you on your toes. The space hoppers seem to form on the filaments, and this was where we tried to pull it all together. So this was our idea. What you get is you have all of this chaotic structure, kablooey nebulae and big holes and being blown around. You've got magnetic fields going through it all, and that rips the clouds apart. But rather like when you're ripping material, it kind of rips into filaments. And those filaments, the directions of them tend to be, whoops, I didn't intend to do that, tend to be determined by the magnetic field direction. Typically they're perpendicular to the magnetic field direction. And these striations typically lie along the magnetic field. So what we think is happening, to get to the punchline finally, is material is flowing down these magnetic field lines onto the main filaments. And once it's on the filaments, that's when you can get enough mass together, enough density to make the space hoppers. Okay, on the filaments, particularly at the junctions of filaments, but generally speaking all the way along them. And so going back to our picture at the start, our textbook cartoon before Herschel, we think the picture that goes before this one, top left, for where all the space hoppers are, is this one. And this is how you form the cores in the first place. You get the material flowing in, and actually once it's on the filament, if you get a slightly denser patch here, it tends to attract material from either side along the filament. And that's what allows the cores to grow. That's what allows the mass to get sufficiently high that the space hopper eventually collapses under gravitational collapse. And so we would modify this picture slightly by putting filaments in here, but basically after that we then agree. And we've explained where picture number one comes from in the first place and how you get to it. So I'm just going to finish by returning to the other question I asked at the start, which is what determines the masses of stars. And there's a lower limit as well. I talked about the upper limit being set by neutron stars and supernovae and black holes and so on. The lower limit is what's known as a brown dwarf. And a brown dwarf is kind of a failed star. If you haven't got enough mass together when the space hopper has collapsed to the middle, you don't have enough mass. If you don't have enough mass to switch on hydrogen burning, then it's called a brown dwarf. As you know, hydrogen burning is what happens in the centres of all stars, including the Sun. And just to give you the scale, here's an artist's impression, the size of the Sun. Here's a low mass star. Here's a brown dwarf. Basically, there's Jupiter and the Earth to the same scale. This is just an artist's impression of a brown dwarf. Something like 8% of the mass of the Sun. So just over 10 times smaller, and you don't have enough mass to switch on hydrogen burning. That's why we don't see stars lower mass than that, because you haven't got enough mass together, you haven't got enough pressure to switch on that nuclear fuel in the centre of the star that's necessary. So that's why you've got a lower limit to the masses of stars as well. And in fact, those of you who've read recent issues of Popular Astronomy will have read my article that I wrote in there about how we discovered one of these things with this telescope here in the French Alps, radio telescope, this rather unexciting looking object here. We actually showed that it's a space hopper, it's a core, but with the mass, only enough mass to form a brown dwarf. This actually appeared in Science magazine last summer, about 12 months ago. And what we proved was that brown dwarf stars can still form in the same way as ordinary stars. That was the first time one of these space hoppers had been seen at that sort of that size. But still, because of a lack of density inside, it's still a lack of pressure inside, it's still got enough mass to collapse. But it'll form a brown dwarf. And I'll finish by talking about planets, because once we've got to brown dwarfs, we've got to the lower limit. What's the next thing down the scale? Well, it's planets. This is, believe it or not, a Herschel image of Fomalhaut, Alpha Piscina Austrina, I think it's called. And here's the star, and then here's this lovely looking ring around it. You'd think it was a picture of Saturn almost, wouldn't you? Except the scale of this is about equivalent to the scale of the Kuiper belt. around the solar system. What we believe we're looking at here is a kind of, or Edgeworth-Kuiper belt to be specifically correct, Edgeworth-Kuiper belt around Fomalhaut. Why do we get excited about that? Well, that gives us the idea that in this gap in here, there are more planets. Okay, and maybe even a shepherding planet over here that's shepherding this slightly denser bit in the ring. Just in the same way as the shepherding moons around Saturn, shepherding the rings of Saturn. It's a similar sort of idea, but obviously on a much larger scale. This is the size of the whole solar system now. And of course, as you know, what we're all after at the moment is an Earth-like planet in the habitable zone. What you sometimes see here called the Goldilocks zone. Not too hot, not too cold, just right. Just right for liquid water to exist on the surface of that planet to allow life to evolve. And so this is our kind of classic picture of that. The red is too hot, the blue is too cold, and the green is the Goldilocks zone. If you've got a very hot star, a slightly more massive star, the habitable zone is further out. If you've got a sun-like star, well, the habitable zone is approximately where we are. If you've got a cooler star, the habitable zone goes closer in. And it's all to do with the amount of energy coming out from your star as to when you're the right distance away from that star to be at the right temperature. And somebody pointed out that actually this is all well and good, but something like 2/3 of all stars, all main sequence stars that we know, live in binaries. And if you've got a binary star, that's going to completely muck up this picture, isn't it? Well, you have a think about that, and various clever people have thought about it. And yes, it does muck things up, but only in certain circumstances. It depends how far apart the two binaries are. If they're close, says, by the way, 0 to 3 astronomical units, so anywhere up to about 3 times the Earth-Sun distance, you can actually still form a disk around the outside of that binary. And of course the disk, that's where the planets are going to form, and you can actually have potentially a habitable zone in that disk around the binary star. If the stars are a bit further apart, so something like 3 to 50 astronomical units apart, then I'm afraid the original ideas are right. You're not going to form a disk because each star messes up the disk from the other one. Okay? You don't form a disk, and they're too far apart for this structure to be stable. So those binary stars we don't think will have planets. Those in that separation. So you have to factor these factors in to when you're trying to work out how many Earth-like planets you might, in the habitable zone, you might expect in the galaxy. Finally, if you go to very wide binaries, more than about 50 AU apart, then it doesn't matter, you just form a disk around each star. Don't know why they haven't drawn one around this star as well, but you can, around both, as if each other wasn't there. So, yes, binaries do complicate the issue, but not as straightforwardly as, if you want a straightforward complication, not as straightforwardly as you might think. And I became fascinated by this kind of idea because I think it's quite an interesting one to follow, because then the habitable zone is determined by the combined radiation from the two of them put together. So it can be quite a long way further out. So this disk can be quite big, but you could still form habitable planets all the way out here. And this is an artist's impression of what that might be like. Here's your binary star going around each other. We're looking at it edge on, of course, or nearly edge on. Here's the Kuiper belt in such a case, and in here you've cleared it out and you've formed some planets, one or more of which may be in the habitable zone. Does that look familiar? You ever seen a planet like that before? Yeah. When I first saw that in the pictures, in the, what was it, 1970, whatever it was, I thought, what a load of tosh. That cannot possibly be stable. Okay? But of course it can. We now know that it can. You can form Tatooine-like planets around binary stars. And so maybe Luke Skywalker's sunset isn't as fanciful as we first thought. So in conclusion, you've got all of these interstellar clouds in space. They rapidly become filamentary. Herschel's shown us that everywhere you look, you see filaments. But it's because of these filaments that you can form the cores, the space hoppers in the first place. If you get enough mass into them, they can collapse and form stars, and the planets then form around the stars. Binaries can mess the picture up a little bit, but not as much as we at first feared. And just in conclusion, I'll just say stars are the size they are for very good reasons. And I'll stop there. Thank you.
Any questions for Derek?
Do we have any idea why sometimes we have some binaries as opposed to superstars?
There are as many theories about that as there are theorists. In fact, slightly more. Lots of ideas. Basically, they all boil down to the idea of angular momentum in the cloud. You're all familiar with angular momentum. You know the old one about the skater spinning round. She pulls her arms in and she spins faster. Smaller things spin faster. It's to do with the amount of angular momentum in the cloud. If there's not too much, then the stuff can get to the centre and the disk can take the angular momentum. If there is too much, then it breaks up on the way down and forms lumps on the way down, and that's what forms your binaries and your multiple stars. As I say, that's most of the theories share that sort of idea in common, but we don't know the details, and as I say, there are as many different theories as there are people thinking about them.
Another question over there?
Oh, sorry.
Over here.
Just going back to the first part of the process, which you've got on the screen there, the initial interstellar clouds.
Yeah.
I take it that they are the result of nova or supernova explosions, are they?
Yes, that's right. I didn't actually go into that bit. We basically think the galaxy is a kind of giant recycling machine. That's the way to think about it. And it goes through several generations of stars. And as each generation turns supernova, it throws material back out into interstellar space, and that material then forms the next generation of stars, and so on. So it's like a life cycle. Like when you remember you learned about the life cycle of the frog when you were at school. This is the life cycle of a star, and the death of one generation of stars tends to generate the birth of the next generation. And where these things tend to form is in gravitational potential wells, which is what we think is defined by the spiral structure of a galaxy. If you look at the spiral structure of a galaxy, we think it's the spiral arms that are defining those gravitational potential wells. Material falls down into the gravitational potential well and it collects there, and that's what forms the spiral arm-like structure. And that in there, that's where you form the molecular clouds that exist. And I showed you that with I think the very first picture where I showed you Andromeda. You could see all of the spiral arms. I didn't point it out, but you could actually see the individual clouds like little dots along those spiral arms. Obviously, because we're looking at Andromeda, we're looking at a much huger scale of material. But that's the clouds as a whole forming in the spiral arms of typical spiral galaxies. There was another question over here.
You said what distinguished a brown dwarf from a star. It's basically hydrogen burning.
Correct.
But what distinguishes a brown dwarf from a planet?
Excellent question. Excellent question. I've been to entire week-long meetings where that question has been debated. As you can imagine, it was highly topical around the time they were trying to redefine Pluto. And there was I was at the IAU General Assembly in Sydney, where that definition was redefined, shall we say. And I won't say they were quite thumping each other in the aisles, but it was quite a heated debate. My favourite story about that, by the way, was I got back and I was in my my local pub, and a friend who knows I'm an astronomer came up to me and he said, "So tell me, Derek, so where the hell's Pluto gone?" He thought it wasn't a planet anymore because it had left the solar system. I said, don't worry, the people on Pluto don't care what we call it. They still think they're on a planet. Basically, the definition comes about, there are lots of definitions, but the most useful one is to do with how they form in the first place. You can form brown dwarfs in the disks around stars, just the way you can form planets. But more likely, and this was what our observation showed, you form them on their own from just little space hoppers, basically just the same way as stars form. Now, that's not a very useful observational definition, I grant you that. And sometimes people see objects and they call them free-floating planets. You've probably heard of some free-floating planets. The idea is they were formed in the disks around stars and then were ejected. But because of that formation mechanism, you tend to get a different interior structure in a planet than in a star. In a planet, you get a more segregated structure, if you like. So maybe a solid core and a gaseous surround. Whereas a brown dwarf, like a star, has a fully convective interior, even though it's not burning hydrogen. Again, that's not a very useful definition from an observational point of view, but it's more a philosophical question, really, because they occupy overlapping ranges of sizes, masses, and so on. The answer I've given you is sort of what the majority of astronomers, I think, would say. But if you were just observing one, very, very difficult to tell when you're looking at a brown dwarf and when you're looking at a free-floating planet.
I've got a question, and that is, what causes the magnetic fields? What generates the magnetic fields in the filaments?
Very good question. Basically, whenever you've got a magnetic field, all it means is you've got a charge moving somewhere. Anytime a charged particle moves anywhere, it creates a magnetic field around it. So whenever you measure a magnetic field, it just means you've got a charged particle moving somewhere. So some fraction of the gas in interstellar space is charged. We call it ions, ionized. And it's that fraction that's generating the magnetic field. Now, what makes the magnetic field so ordered? That's another huge question. There are lots of theories. My favourite one's to do with what they call the galactic dynamo. You've got this gigantic structure 100,000 light years across. We call it the Milky Way, and it's rotating. The stuff further in is rotating faster than the stuff further out. So you've got, that's known as differential rotation. You're familiar with that idea. So the charged particles are moving at different velocities at different radii from the centre. You can model that as one gigantic dynamo that generates these huge, actually quite well ordered magnetic fields across the whole plane of the galaxy. And these have been measured in polarization measurements. They've been known about for a number of years, several tens of years in fact. 76 was one of this sort of classic papers looking at just the polarizations of stars, and you see this really, really well ordered magnetic field going right across the plane of the galaxy. Now obviously the magnetic field is slightly tied to the matter, again because it's ionized, so as the matter moves around, not only does it generate magnetic field, but the existing magnetic fields, it also tows them around with it. So the magnetic field gets kind of tied up with the matter. So as the matter collapses to form the filaments, the magnetic field gets strung out perpendicular to the filaments, it then acts like a funnel, acting back on the matter to funnel the material down onto the filaments. Yes, the two are completely interrelated,
Right.
and that's the idea of how it works.
Any more questions? There's one last question there. Yes.
Yeah.
Do I understand from what you have said so far that mass attraction is the current is the core of all attractions?
Yes, that's correct. That's correct. Eventually, gravity always wins because we don't know of any anti-gravity, basically. In electric fields, you've got positive and negatives. In magnetic fields, you've got north poles and south poles. Gravity just attracts, and it goes on attracting, and there is no limit to how far you can go, and gravity is still attracting. It is an infinite force. So ultimately, gravity will always win if you get enough mass together, and that's what the neutron star experiments tell us. That if you get enough, you can even overcome the strong nuclear force.
Has mass then been used in the calculation of the masses of the universe?
Yes. Yes.
Otherwise, there is no way to do that.
That's right. It's yes. Okay. That was probably the most approximate number that I showed you today. Okay, the mass of the whole universe. But we can make estimates because we know roughly how massive each galaxy is. We know roughly how many galaxies there are per million light years cubed, and so on. And so, again, by the sheet of paper argument I told you about our galaxy, we can work out roughly, how many galaxies there are. We know the universe is about 13.7 billion years old. So that's why I very carefully said the observable universe, you notice. The observable universe is about 13.7 billion light years across. So you just multiply how many galaxies per cubic light year by 13.7 cubed.
It could have been completely different so many years ago.
It could. It almost certainly was.
Well, at that point, looking at the universe as a whole, if you'd like to return your thanks again to Derek for describing how everything happened.